Hello there, and welcome to Module 7. So let's kickstart and understand some areas where we are looking at modeling and designing in a manner that we will be able to get to effective test cases. So let's see what we have in Module 7. So Module 7, in fact Module 7 and 8 are two parts where we are doing module-based testing. We'll look at what module-based testing is, its introduction, overview, our perspective. Then we look at finite state machines and the fault model. In fact, up till now, all the techniques that we have been looking at have been equivalence class, boundary value analysis, decision tables, and we've always been thinking about how do you bring in the stateness. Statefulness is what will help us understand many systems. For example, traffic light that we spoke about is so stateful system. And then, of course, we're going to look at examples and a small case study. So let's kick in. 7.1, that's what we have, our first topic, model-based testing, introduction and overview. So at this point in time, a question for you. What do you mean by model-based testing? What model are we talking about? You may want to take a pause right now and find out what modeling really means. You may want to search the internet or look up information from your sources to understand modeling and model-based testing for us. So we will also enter into the arena of design. Design, as we looked up even when we are looking at requirements analysis, in fact, some of the area where we will see that design could form a basis of implementation and design could form a basis of test as well. So this module actually stresses on that. So what is model-based testing? One is we actually put a model together for a particular system, which would mean that we have got better insights into understanding the system. We get a deeper insight as to what the system is going to be. This would be through requirements analysis, or in fact, even understanding the system's needs, the way the system is going to be used. You would appreciate that there are various models. Models keep evolving. Models have been evolved over the past decades. And our understanding, our representation of the model, and the accuracy of the model itself will give rise to the adequacy of model-based testing. So is it adequate? Is it enough? This all will depend on the model that is chosen. So it will depend on model that is chosen. Second thing is our understanding of the model and our use of the model. So what sequence do we follow? Typically, what would be the sequence that we follow? We model the system and we look at systems behavior. I think one of the keywords to look at is systems behavior. Now, what do we mean by this behavior? So let's look at two examples. Right, let's discuss on two examples. I have an ATM, automated teller machine, and let's have a coffee machine. What would an automated teller machine be? What would it do to us? What would it do for us? I enter the credit card or I enter my debit card, punch in numbers, it connects with the server, gives me options to withdraw, to deposit, or to find the balance in my account, and so on and so forth. So each of these becomes states. The machine is in a state of waiting for input from the user. The first input would be the card. So I insert the card, and then it is in a state of waiting for the PIN. The moment the PIN is entered, it is in a state of processing the information and finding out that I'm indeed the person who's authorized to do any operations on this particular account. So all of this give rise to how the system is behaving, and it is a state-based stuff. And now all of these form understanding of the system for us. Representation in a pictorial format in various manners will allow us to understand the system better. And as we go on revising, as we go on iteratively looking at the system, we will not only get better understanding of the system, but a better model, and in the end, better test cases. That's what model-based testing is all about. So how do we really represent? Our representation is in three mechanisms. In fact, you would see one of the animations also on your screen, which is of a Petri net. So there is an animation for the Petri net over here. You would see the states and places and enabling and disabling happening. And you would have looked at some amount of Petri nets in your mathematics module. So we see a mechanism to represent is finite state machines and also state charts. Detail orientation changed from one model, one representation to the other. And that is how these executable models came into being for not only better understanding of the system, but better derivation of test cases for us. And we will look at the finite state machines as a model for us in this particular module. So what this whole modeling is around? So modeling is around two things: what system is, and the second part that you would see is what the system does. So there are two parts: what the system is. Now what do we mean by what the system is? So system is by its components, by its functionality. And of course the system would have interfaces. So if I have a ATM, it would have an interface that it works with the bank. It would have a UI, a credit card slot, a printer, a cash dispensing area. And functionality is withdraw money, check balance. Components are going to be components which are to do with the user interface. Let me change the color. So we'll get user interface, we'll get credit card, cash dispensing, print dispensing, and of course many times you will also find a camera out over here, so it is picking up visual cues, who's operating the ATM, so on and so forth. So what the system is, what is the system comprised of? And this all is emphasizing the structure of the system. It is like a building. Building has a structure. It will have a RCC structure, a foundation that can take a total of 3 floors or 5 floors. So it becomes a structure. The second part is what the system does. What the system does is all what is defined using things like decision table, state charts, Petri nets, finite state machines. What they describe system behavior. How does the system behave? This is where systems' expressive capabilities come into the being. Expressive capabilities. This is what the system is going to behave. If you enter the credit card PIN 3 times wrongly, your credit card may be blocked, or it's going to eat up the card. Those become the behaviors of the system, expressive capabilities of the system. If you do not pick up cash, it is not going to eat up the cash again, but it's going to leave it off over there. That's the notice that I typically read on most of the ATMs when I go to withdraw cash. So two parts, very clearly defined, two parts, and I've just put it up on one page where we are looking at what the system is and what the system does. One emphasizes structure, the other emphasizes behavior. It's about components, their functionality and interface. Here it is all about behavior. We have got a lot of other ways of representing it. Data flow diagrams, class diagrams, hierarchy charts, entity relationship models. In this case, it is decision tables, finite state machines, state charts, Petri nets. That is how we would define it. So this becomes the system model. What the system is and what the system does. So don't you think this is a very fundamental mechanism of first understanding the system? Now match this up with those 8-step process which we looked at in kind of understanding the system inputs, the type of inputs very deeply. And if you have done the self-study where you're looking at elements of system testing as a test engineer, then you now know that this is a big time tool, the modeling part, to understand the system. Now, one way to see is that there is a system which is specified, and then there is requirements analysis that happens, and then there is a model that gets derived of a system. And this model may be commonly used for development and commonly used for test. But that's not a must. It could be so that we have got a system already present over there, and you look at the system, so you review the system, and you come up with a model of a system. Now, this does not mean that this model is equal to how the system is designed, but this is how you view it based on the usage of the system, based on your belief as a test engineer how the system would be. So one is requirements analysis, design, and this model is used for development, model is used by test. That is one way of looking at it. The other is you model the system based on your understanding of the system, which need not lead to the way it got implemented. In fact, a system may be implemented with non-object oriented software, but you may have entire modeling based on object orientation. And in fact, we'll look at that aspect in one of the very small examples, but very profound examples later in one of the topics in this module. So model-based testing, one part is now you have understood the system, you're able to model it, there is a state chart, you know what the system is, what the system does. Ultimately, we would want to have ways to generate test cases. And if they can be generated automatically based on the model, wow, that will be great, because then that gives you a notion of completeness. And also, since it is based off a model, the coverage also could be commented on because it would be as accurate as the model. So I spend as much time on the model, I would be able to get those many number of test cases. And of course, completeness would be something that the system would take care of for me. So here I give an example of a graph walker. You may want to take a look at it in your spare time, which is a model-based testing tool. It actually helps you generate test cases from a model, a state machine model. Okay, so that's what we had in 7.1. What we have kicked off is a discussion related to model and model-based testing. We understand the system behavior. We would like to understand what the system is composed of and make sure that we take it forward. Thank you.